see here. Too soon? I'll pray. Heavenly Father, we thank you for this day, and I thank you again for this class and this opportunity we have to meet and study your creation. I just pray again that you be glorified in what we do this day. And we just thank you again, Lord, for your many blessings. In your name I pray, Lord Jesus. Amen. All right. Nope. Maybe. Nope. 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 Sorta. Nope. Well. Nope. 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 Okay. Partial. All right. Well, 2/3. Nope. Sorta. Well, half right. Nope. 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 Well, Nope. Nope. Okay, so this begs the question, why am I teaching you power series solutions when you don't know what a power series is, right? Like, so you'd be like, well, I didn't tell you to study for that. I shouldn't have to tell you to study for it. You should know the basic power series from calculus too. I mean, I don't know. I guess there's this like philosophy, like once you have the course, you can forget about it, right? But I don't know. Maybe it was 5 years ago for you, whatever. But let us address the elephant in the room. What are the power series for like functions that we know? For example, e to the x, the power series. The Maclaurin series for this is the sum. Anyway, I had a feeling it was this way, so that's why I gave that quiz in part. And those are bonus points too, right? So if you didn't get those, you could still got 10 points from the stuff we did last class. And a point for your name. But this is the full Maclaurin series for the exponential function, right? And so I think the first three terms in this are 1 plus x plus 1/2 x squared. And that's, what's next? Here's the first four terms. 3 factorial, right, which is 6. So this is the exponential. Cosh and sinh are what? We could say k equals 0 to infinity of x to the 2k divided by 2k factorial. So what that is, you know, the even terms in the series above, right? Sinh, on the other hand, is x to the 2k plus 1 divided by 2k plus 1 factorial, which goes like x plus 1/6. Well, I'll put a 3 factorial here for emphasis of pattern. X to the 3rd plus 1/5 factorial, which is 120. X to the 5th plus dot dot dot, right? So power series for exponential, power series for cosh, power series for sinh. If you add cosh and sinh together, what do you get? You get the exponential, right? These are exactly the even and odd terms of the exponential series. And then, of course, we have other things like cosine of x, which is the sum k equals 0 to infinity of like minus 1 to the k divided by 2k factorial x to the power 2k, or sine of x, which is the sum k equals 0 to infinity minus 1 to the k over 2k plus 1 factorial x to the 2k plus 1. So both sine and cosine have like alternating series of sorts. Of course, is this really an alternating series? Well, that kind of depends on if the absolute value of x is positive or negative and stuff like that. But it at least appears to go plus minus, you know. Let's see here, x minus 1/3 factorial x cubed plus 1/5 factorial x to the power 5, right? So these are the major players in this game. Everybody should know these, all right? And if you don't, that's okay, but now's the time to learn. And then the other thing, of course, is that you can use these to create new series from old, right? Substitution looms large in my example set. So for example, like I did on the quiz today, sine of like x to the fourth, you do what? I like think of it this way. Okay, so this is sine of theta with theta equal x to the fourth. And if I write the power series for sine, you got theta minus 1/6 theta cubed plus 1 over 120 theta to the power 5. And then you just plug in. So this is x to the power 4 minus 1/6 x to the fourth cubed is x to the 12th. 1 over 120 x to the 4 times 5 is 20, and so forth, right? Yep.
So is it okay if we had like the original series for sine and then put x to the fourth on the outside?
No. I don't think you can do that. No. I mean, you got to plug it into where the x goes. Sine of x times x to the fourth would be a different thing, right? If I just take this and multiply by x to the fourth, that gives me the series for x to the fourth times sine of x. Like, that's a decent example, but it's a different one, you know? If I take like x to the fourth times the sine of x, I can just multiply this down here by x to the fourth, and I get, you know, x to the fifth minus 1 over 3 factorial, you know, x to the 4 plus 3 is 7, 1 over 5 factorial, 5 plus 4 is 9, right? So yeah, we can also multiply series by like a monomial. You can also multiply two series and like do you know, expand order by order. That's something else we learned in Calc 2, right? So we'll have to do those things as we solve differential equations. So if you're super rusty on this, which I think is fair to say you are, you know, maybe it would be a good time to crack open your Calc 2 notes or something, see what you did back there, that kind of thing. And then the other thing that I used on the quiz just now, because this is also like an example of examples, is the geometric series, right? So the geometric series says a over 1 minus r is the sum n equals 0 to infinity of a r to the power n. Supposing that the absolute value of r is less than 1, that defines the, you know, where that series converges, right? So specifically, this is what, like a plus ar squared plus dot, 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 forever and ever, amen, right? That's the geometric series. So for instance, if I have x to the power 35 over 1 minus x to the 14th, what'd I do? 7? 3? All right, so that is, notice that you could factor the a out, right? You could just factor the a out, but I guess I won't. So so identify what's going on here. A is equal to 35, right? A is x to the 35, rather. And my ratio is x cubed in this case. So I just do, you know, a, which is x to the 35, and then plus x to the 35 times x cubed, plus x to the 35 times x cubed squared, and so forth and so on. So like the answer to that part of the quiz was x to the 35 plus x to the 38, and, oh, what do you know, plus x to the, what's, oh man, I messed up. Only 41. What the, oh, come on. Well, anyway, I'll do better next time. So, you know. Sorry, this is a stupid example. Now, I have no regrets. What's the thing you might remember from Calc 2 about power series? Do you remember this? Taylor's theorem said what? It said we can write f of x as the sum n equals 0 to infinity of the nth derivative evaluated at x naught, let's say, over n factorial times x minus x naught to the power n. This is what Taylor's theorem said in brief. If the function's analytic at the point, in other words, if it's well represented by its power series, then its power series can be generated by Taylor's formula as such. But while this is, of course, of great theoretical importance and use, it is of limited application to actual finding power series of Maclaurin series of like specific functions, right? Because I don't know about you, but the task of applying, think about this, to apply Taylor's theorem to derive this example that I have right here. This one over here. This one over here. This one over here. Thank you. Sorry. If I was to apply Taylor's theorem directly, how many derivatives would I have to take? I'd have to take 20 derivatives to get this 1 over 120. See that? And those derivatives, by the way, are unpleasant. Because after you differentiate the first time, chain rule pulls down to 4x cubed. Then you're doing product rule. And products of products. And products of products of products. And products of products of products of products. And so forth and so on. If you don't simplify, right? So direct use of Taylor's theorem is unwise here. This substitution idea I'm sharing with you here is like super important. Also, this is a very important idea, like multiplication of a given. So really, if there is any way you can use the known Maclaurin series, you need to do it, right? But this is our get out of jail free card. Sometimes we can just use Taylor's theorem. All right, so there you go. That's my my 2 cents on Calc 2 stuff that maybe you're a little bit rusty on. Let's get back to the differential equations. So example 1. What if we were trying to solve y prime plus 3y equals to, oh, I don't know, e to the x cubed with y of 0 equals to 1. Let's find power series solution to order, let's say 4, centered at 0. All right. So how do you do this? What you do is you suppose that you've got a power series for your solution. You say, right, y is equal to, a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the 4th. That ought to do it, I think. So there it is. There's a power series to order 4. Now I differentiate it. And we're just differentiating term by term, right? Everybody here can do that, right? Now we plug these into the differential equation, all right? And here's where it starts to get a little bit interesting, right? So we've got, I'm just going to write it out symbolically if you guys don't mind. I better write it out. Rats. So y prime plus 3y equals e to the x cubed. All right. Notice that e to the x cubed is 1 plus x cubed plus 1/2 x cubed squared, right? Now we're not going to need the third term there because that's order 6, right? The first 2 terms should suffice, I think, in this calculation. Y prime, so let's write down what we got. We've got a1 plus 2a2. What am I missing there?
X.
Yeah. Thank you. All right, plus 2a2x plus 3a3x squared plus 4a4x cubed. These are all my y prime terms, okay? And then I've got plus 3 times y, which is there's it. That's my y terms, right? There's y. And that's all equal to 1 plus x cubed plus 1/2 x to the power 6. But again, I probably won't even care about that 6th order term since I haven't taken the time to write down the 6th order terms in the other part of it, right? Okay, so then what? Well, you guys have been doing undetermined coefficients for a little bit, so you're used to the idea of equating coefficients, right? It's just now, instead of having A, B, C, D, we have A0, A1, A2, A3, A4, A5, A6, A7, A8, A9, A10. We could go on. You've got infinitely many undetermined coefficients, but the technique is pretty much the same. So we just go order by order, right? Like start at the, well, actually one other thing. But y of 0 equals to what? It's given to be 1, but what else is it equal to? What happens when we plug 0 into y? All this stuff goes away, right? Gone, 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 gone. We're left with a naught. So, well, there's one for free. Since we're given an initial condition, we actually already know that a sub naught is equal to 1. Hooray. So you can either do that at the start or at the end. All right? I'm going to do it at the start since we did it. OK, so constant terms, probably we're not going to get any more information there, I don't think. Maybe we will. We've got what? A1 plus 3a naught. Anything else constant? Equals to what? It equals to the 1 over here, right? But we know that a sub naught is equal to what? 1. So this tells me a1 is equal to what? -3 or -2? We got to come to a consensus. Math is done by consensus. What's the consensus? -2. OK, very good. OK. You know, Trump's in Roanoke this Saturday. Tempted to go. What do you think? I don't know. That's like the day before. What is it? That's not the day before the election. Who told me it was the day before the election? That makes sense. The election's got to be on Tuesday, right? How about x? We've got 2a2 here. And how many other x's do we got? Over here, 3a1, right? Plus 3a1. There is no x term in the forcing function, so we get equals to 0 in this case. Right? And let's see here. So that tells me that a2 is equal to what? Yeah, -3a1 over 2, which you guys told me is what? Is it 3? 3. OK, 3. All right, great. Now up x squared. What do we got at x squared? For x squared, we've got 3a3 plus 3a2. And nothing over here equals to 0. So that tells me that we got a3 equals to what? -3? Well, this would say that a3 is, this would imply that a3 is minus a2, right? Which I think is -3, so. Because you can divide by 3 and you get that a3 is minus a2 there, right? Now for x cubed, what we got there? For x cubed, we've got 4a4 plus 3a3. And, oh, we got a 1 on the other side equals to 1. So apparently, a4 is equal to 1 minus 3a3 divided by 4. Let's see here. a3 was -3, so that's 1 plus 3. No, 1 plus 9 is 10. 10 over 4. It's 10 over 4, right? Yeah. Also known as 5/2, right? And that's enough, because I just had to find it to order 4, right? So we've got the order 4. We can stop here. Therefore, y is equal to 1 minus 2x plus 3x squared minus 3x cubed plus 5/2 x to the power 4 plus dot, 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 dot. This is a power series solution to the differential equation. No need for undetermined coefficients or annihilator method, right? And we're finding the homogeneous and the particular solution all together all at once in this method. And the method is, to summarize, very dumb, right? We take a power series, we plug it in, and we work it out. That's it. Yeah? It's not too bad. Let's make it worse. So let's do the full power series solution. So up to now, I've just did a couple of examples where we had, what's the word? We just worked out the first few terms, right? But sometimes we are interested in finding the complete power series solution. And to do that, we need the summation notation. All right? And there, we need to think about some calculations that maybe we haven't thought about in a little bit, but we can do it. So I'll start by working out an example which should be familiar, and we've worked out a different way, all right? But I'm going to work it out from the theory of power series because it's a good starting example. We'll try a harder one next class probably. So example 2, we could try something like y prime prime, let's say plus 9y prime equals to 0. Ooh, not y. I didn't mean to put a prime there. 9y equal to 0. Again, we could do this with the other method. I'm using this example because it makes the power series analysis a little bit easier to track. I can't do it. Let me make it something we can't solve. Make it something we can't solve. I'll throw an x in here. There. Now it's unpleasant. Like, you can't solve this with our previous methods, right? So what do? We let y equal to the sum n equals 0 to infinity of a n x to the power n. And then we differentiate. N equals 1 to infinity of n times a sub n, x to the n minus 1. And then we differentiate a second time. All right. So you notice why I have n equals 2 here and n equals 1 here because I can, right? The initial terms are 0. If I was to keep the n equals 0 to infinity, it would be adding 0 at the start of the sum. So I don't want to do that. All right, so let me plug it in. Again, it's just that dumb. We're just plugging it in there, but we got to work it out carefully. So we have the sum n equals 2 to infinity of n times n minus 1 a sub n x to the n minus 2 plus x times the sum n equals 0 to infinity of a sub n x to the power n. All of that, 0. This time we're working a homogeneous problem. In fact, I'm pretty much just going to work homogeneous problems from here on out. The non-homogeneous problems are worked pretty much in entirely the same way. It just complicates the issue a little bit. So we're going to focus on homogeneous problems pretty much. That is sufficient for my mission of confusing the students. It works. It's quite enough. So, all right. So then what? So if you'll allow me to save some board space, I'm going to make a small modification with my handy-dandy red marker right here. I'm going to trade multiplication by x for n plus 1. All right? Does that make sense? I hope it does. Because that's how we multiply a series by x. Yeah.
I think you're going to do it in the next step.
Oh, okay. Now, I can't just add these series, right? Why? Like, yeah?
The indexes are different.
Yeah, the indexes are different. It's kind of like adding apples and oranges, or Democrats and Republicans. I don't know, whatever you want. But I'll try to find some more morally neutral example. That's right, I said it. I said it. Sorry, I'll behave. I was going to wear my Trump hat today and make it MAGA Monday. I forgot though. I really hope that we know the election before Christmas. Anyway, so what we're going to do is we're going to let J equals to n minus 2 for this one. And we're going to let J equal to n plus 1 for this one. Right? If I do that, then that will make these look the same, right? Notice, though, that J equals what? 0, 1, 2, and so forth for this summation, right? What's J equal over here? It starts there, right? If n starts at 0, J starts at 1. So I don't even have any hope to combine these at every order, right? Because they don't share every order. Notice that this right here is an outlier, right? That's an outlier. So we're going to have to write that before everything else. So we just write it over, n equals, J equals 0, corresponding to n equals to 2. We get, 2 times 2 minus 1 times a sub what? 2. All right? And then plus the sum, J equals to 1 to infinity. All right? Now, if J equals n minus 2, what's n equal to? J plus 2, right? So I have J plus 2 times J plus 1. A sub what? N, A sub n, but A sub n is J plus 2. Right, then x to the power J. Then over here on the other one, I've got the sum J equals 1 to infinity. Let's see here. How's this one go? Trying to find another marker. This one says n equals J minus 1, right? So I have A sub J minus 1, x to the power J over there. And all of that equals to 0. All right. Now we have overcome the partisan divide of the previous formulation. Now we can all join together in one grand party. One single party for all. Wouldn't that be great? Nobody has any freedom to choose anything other than anybody. Everyone forces their will upon everyone else. It's just perfect. Let's see here. So 2a2 plus the sum J equals 1 to infinity. Let's see here. And then we've got ourselves, I'll write it for J plus 1 times J plus 2, A sub J plus 2, plus A sub J minus 1, all times x to the power J equals to 0. So what do I learn from all this? What does this tell me?
We can shift indexes.
Well, yes, this is an example of how we can shift indices, but why is this of importance to us? Like, what does this do for us now? Now we have everything cleaned up, right? So we can clearly identify what's the coefficient of each power, right? And we can equate coefficients to 0. So like, for example, we have 2a2 equals to 0 from like, the constant coefficient, right? What do we get from the xj coefficient, x to the power j? Well, we get that j plus 1 times j plus 2 times a sub j plus 2 is plus a sub j minus 1 is equal to 0. And that's for what? That's for j equals to 1, 2, 3, and so forth and so on, forever and ever. Right? Well, the first one's easy enough to solve, right? I think we can all agree that a2 equals to 0. Right? So there you go. That's good to know. All right? But what about the rest? What do we do? We just have to do the algebra, folks. But the algebra may be unfamiliar to you, so let's look at it. So what we have, I'm going to reformulate this equation here. I'm going to reformulate star yields. I'm going to change to n. I just like n more. So we've got a sub n plus 2 equals to minus a sub n plus 1. Oh, n minus 1, right? Divided by n plus 1, n plus 2. I still don't like it. I still don't like it. I don't like it yet. Because I don't like to have a shifted index on both things. It's just for the purpose of analysis much easier if we can make one or the other of those an unshifted index. So what I'm going to do is I'm going to trade out, I'm going to write a sub n plus 3 minus a sub n what? Well, just a sub n, right? So what I'm going to do going from here to here is I'm replacing n with n plus 1. All right? So I'm just rewriting the formula with n going to n plus 1 to make the formula easier. So then n plus 1 goes to n plus 2. And n plus 2 goes to n plus 3 in this system. And then you should just check that the pattern still makes sense, right? This n plus 2 matches that n plus 2. This n plus 3 matches that n plus 3. And the difference in the subscripts is like 3, right? All right, doing this is just going to make our life easier in what follows. And this is true for what? We had over here j was equal to 1, 2, 3, right? But I think this, trying to think. So a sub 0 was the lowest coefficient over there. I think this is good for n equals 0, 1, 2, and so forth. All right. We good? So let's try to wrap this thing up here. So we've got, a sub 3 equal to minus a sub 0 over what? Yeah, 6. 2 times 3, right? So minus a sub 0 over 6. And then we have a sub 4 is minus a sub, oh man, well, it's fine. It is what it is. I'm not entirely satisfied. I should have made the, it's too late. I've done what I've done. Let's hear. What I was saying is, I should have made the n go over here. That would have made it easier to think about. Because now I'm going to think, this is like n equals to 1, right? But anyway, this is a 3 times a 4. So minus a1 over 12, a sub 5, minus a3 over 5 times 4. Wait a minute. 4 times 5, yeah. So minus a3 over 20.
Wouldn't it be minus A2? Yeah, A2 plus 3.
Oh, yeah, duh. Sorry, my bad. Oh, but that's easier because that is 0. And then a sub 6 is minus a3 over 5 times 6, I think. But that is minus a0 over 5 times 6 times 6. A sub 7. Let's see here. Minus a4 over 6 times 7, which was minus 1 which is a1 over 6 times 7 times 12. So what you should start to see is that we're going to have what? Do you see what's going to happen? We're going to have all of the terms that have the form like multiples of 3, right? Like this one, and if we were to go down to a sub 9, right? Those are all going to end up picking out an a sub 0, right? They're all going to have a sub 0. And what else is going to happen? We're going to have a sub 4 and a sub 7, and if I had written it, a sub 10. These are all going to have an a sub 1, right? And the other thing I can tell you, without further ado, is that if we have, a to the 3k plus 1, well, this is equal to 0. What is it, 3k? No, 3k plus 2, my bad. 3k plus 2. So these are the things like a sub 2, a sub 5, a sub 8, a sub 11. There's a triplicity. These are all 0, starting with a2, right? Because ultimately the star equation links 3 orders separate. But anyway, I'll finish this thought next class, so that's where we're stopping for today. So thanks, guys.